Hello, this is Patrick O'Shaughnessy, and this is the 20th module in the series, Statistical Methods for Analyzing Data Obtained in the Lab or Field. In this third part of the modules associated with laboratory statistics, we'll explore the concept of the limit of detection and the limit of quantitation. Okay, another important concept is this idea of the limit of detection. Now let's get into that. So as you can imagine, it's a limit, just as it says, of being able to detect something by an analytical instrument or any type of instrument. So it's the lowest quantity of a substance that can be distinguished from the absence of that substance, a blank value, with a stated level of confidence. And it's generally a really high level of confidence, 99.7%, as we'll see. So again, every instrument is going to have some random error, some noise associated with it. So you want to have a measurement that gets above the noise so you can truly say, yep, I'm confident that this is something other than what might be zero, right? That it might be nothing coming from your instrument. So that's the idea behind an LOD. So how do you determine an LOD? Well, one way is to make multiple continuous sampling of your blank. Put it in your instrument, keep measuring it. You're actually going to get some noise about zero in this case. And it'll be zero sometimes, it'll be slightly greater than zero, maybe a little bit more than zero. So that will give you some idea of the standard deviation of the instrument at that level. And then you can multiply that standard deviation by 3, which is the typical situation to determine an LOD. And as we just went through, a 3 sigma is equivalent to 99.74% confidence limit. So we know when we're beyond 3 sigma, we are definitely outside of that tail of that potential area within which we might actually be measuring nothing, a zero. So here's kind of graphically, we're looking at the right side of the normal distribution of potential measurements because, of course, in most cases for an analytical instrument, they're not going to give you a negative value. It's going to be 0 or greater. So again, it's highly likely that a measurement greater than 3 sigma is not caused by a sample with no substance on it. So we're trying to prevent a false positive. That's one way to look at it. Okay, another way to determine the limit of detection is with regression analysis. And so you have a sequence of standards that you apply to your instrument of increasing magnitude, say mass of whatever applied to a spectrophotometer, that sort of thing. And again, you can come up now with a standard deviation of the noise, but now it's around your line, right? This slope that you've developed between your standard and the instrument response. And so they call it the standard error of the regression. Again, in the third module on regression modeling, it's talked about somewhat, but definitely in the 5th module. You should look at that again if you aren't familiar with this terminology. So that is the standard error, is the difference between your point and the point on the line. That's the error we're talking about. So again, the LOD now is 3 times something, but in this case, that something is the standard error of your kind of noise around your slope, your linear regression line, divided by or compensated for by the slope value itself, beta 1. So here's an example of, say you have 6 standards prepared for a gas chromatogram in nanograms from 0.1 to 5 nanograms, and the instrument response is this peak area. Okay, so you plot them out and you see a relationship like this. You can get a regression analysis from it, but we need this standard error value, and that is reported by Excel in the data analysis tool pack /regression function. Again, look at Module 5 for that, and you'll see that the standard error is reported here as 603, and the slope is 2,383. So the LOD is 3 times the ratio of those two numbers, and we get 0.76 nanograms. So the LOD is actually somewhere down here. We were able to actually measure values below it, but these two at the bottom here, statistically, we're not sure that they are something other than 0. That's, again, the point of the LOD. So any points above that are good, so to speak. And in order to do this correctly, these instructions, so to speak, are to try to push the envelope downward here and have some values down here as low as possible and string them up in some sort of sense like this and have at least 6 to 10 data points to make a good regression line with it. Okay, so that's the LOD. What about this thing called the limit of quantitation, the LOQ? So this is an even bigger number than the LOD. It's the lowest concentration at which the analyte can not only be reliably detected and differentiated from 0, but at which some predefined goals for bias and imprecision are met as well. So there's no set way, as it says here, there's no absolute way of setting and calculating the LOQ, but it's certainly always greater than the LOD. I've seen LOQ equals 10 sigma seen here, or 9 sigma. So you can see it's way out there on the tail, way out there. And why should it be pushed so far out? Well, this graphic here, actually from Wikipedia, does a pretty nice job of describing that. Where again, here's our 0, and we've just discussed that the LOD is going to be way out on 3 sigma out on the tail of that distribution of values when we're just measuring a blank. And you can see that the LOD, as shown here, is trying to compensate for what's called the alpha error. We don't want, again, a false positive. We don't want to be down in here so low that we say it's something there, but actually it's not distinguishable statistically from 0. So that's a false positive. But you can see here that if we are at a value right at this LOD, and we keep sampling and sampling, we actually have measurements at the LOD, it will vary back and forth, right, according to this distribution here. And so you can see that 50% of those values will have a false negative. They truly are bigger than 0, but they're going to be less than the LOD and declared as being, well, indistinguishable from 0. So that's the false negative. So you can see the issue now is to try to push all of this out so far so that a measurement taken in its distribution and its lower tail area is so far removed from this kind of mess back here that it can be truly distinguished from 0, and you have minimized, certainly the alpha error now is down like way lower than 1%. It's almost impossible to have a false positive out here, but now you've also made it almost impossible to have a false negative, and that's the whole idea behind an LOQ. So now with the definitions of LOD and LOQ, we might take a look at what we get back from a lab if we send samples off for analysis. And the report that comes back will have perhaps additional terms besides just LOD or LOQ, one of which is the reporting limit. And they may define it specifically and they may not. But typically the reporting limit is equal to the LOD times some kind of safety factor that they apply to compensate for variations in instrument performance on a day-to-day basis. So it's a kind of a fudge factor to increase the LOD, but that is getting near to the point of an LOQ, right? That we want to get way above the noise of the instrument and to be certain that the value obtained is a real value and not something close to 0. So it's essentially an LOQ. Another term they will use if there is something that's way down at the bottom of their instrument sensitivity is called just simply not detected, or ND. So in the EPA terms, they would call this below the method detection limit, the MDL. And as we've been discussing here, it's essentially below the LOD value of the instrument. So again, they won't give you a number, they'll just simply report ND. And this brings up the issue of censored data, as the statisticians would call a non-detect. So you're not given a number. So what do you do with that analysis result? Do you just ignore it completely and then you're down a lower sample size, or do you call it zero? The answer to that has been explored over the years, and the typical response is no, don't ignore it, and no, don't call it zero. Give it some value, and the value that's typically applied as the simplest way to get at it is to simply divide the LOD by 2, or if you know you have a log normal distribution of values, they'll use the LOD divided by the square root of 2. And you'll see journal articles discussing this issue, and there's, again, more sophisticated ways of dealing with this, but those are the two simple methods that have been used often over the past decades to compensate for this problem. So here's an example of a lab report that I received. This was on some road dust samples, actually. We were interested in the metals content of the dust. So we got this report back from the lab, and so you can see that they give you a result. They'll also have a column for the reporting limit, give the units, whether they diluted it or not, and other aspects of it. But we're interested again in the result and the reporting limit. And you'll see here that some of them, yes, do have a result along with their reporting limit, and others just simply an ND, but there is an associated reporting limit. So in this case, if you're going to do statistics on this data, you would divide this 1.00 milligrams per kilogram divided by 2, or divided by the square root of 2. You just be consistent across all possible of these NDs that's shown here. Now again, the report should define these terms, and so usually at the very end or someplace in the report you'll see a table. In this particular one, it was not overly helpful. They just stated that the ND is the analyte not detected at or above the reporting limit. Okay, so there's that RL, reporting limit. But as you can imagine, what we've just discussed, they don't define then the reporting limit in terms of an LOD or an LOQ. And here is one additional example of a lab report. In this case, some samples on a filter were sent to a lab that contained ethylene glycol, and we wanted an analysis of that. So I'm just showing you the results here for a blank, and again, you would expect that a blank would be below the limit of detection. That would be the hoped for result, but again, it's interesting with blanks that you aren't given a number. In almost every case, you're going to be given a ND, or non-detect, or in this particular way of displaying the data, they simply put a less than 0.010. So they are kind of combining both of those previous columns. That means that it was a non-detect, but also means that 0.010 was the reporting limit. Okay, so that's the value then that would be divided by 2 in order to include it in statistical analysis again. Now this report had much more information in terms of these various values. They do define a non-detect, but they say it's non-detected above, it's test result not detected above the LOD or LOQ. So hard to determine which one, but they do give these definitions of LOD as being equivalent to this method detection limit, and the LOQ again is in their case equivalent to the reporting limit. So again, it depends on the lab and the way they report these, and if you have any confusion over it, you should call the lab manager and have them explain to you what these various values mean. And by the way, you can often ask the lab for the actual value spit out by the machine, even though the report says below a detection limit, if it's really essential that you have some good idea of what the value actually measured was. Then you could just maybe asterisk it, mark it as a value that is below the detection limit, but something that's worthwhile knowing what value was actually measured by the instrument.